Hi everyone, welcome back. So today we're going to be talking about local stability of first-order systems. So first recall from Chapter 2 and also from our homework from last week that we can use Taylor's theorem with remainder to approximate a nonlinear system of equations. So we can use Taylor's theorem to approximate a nonlinear system. And this allows us to say a lot about local, at least locally. And so this allows us to say a lot about nonlinear systems in a small neighborhood around an equilibrium, because we can linearize around that equilibrium and then look at the Jacobian. In your homework from last week, one of the things we did is we looked at linearization around a point when you only have a single equation. In today's lecture, we're going to generalize that to systems of first-order equations, and of course, we're going to be looking at eigenvalues of the linearization, more precisely the eigenvalues of the Jacobian matrix. So let's start with the usual setup. Let's x dot of t, so a system of equations, or a vector-valued function, be equal to f of x of t. This is a first-order system of first-order equations, ODEs. Actually, let me give this a compare. So this is similar, so compare this against video 2.8. Okay, and we're going to let x of t be a column vector of each of our individual variables, so x1 through xn of t. And we're going to let our function f be a vector of functions, fn of t, transposed, where each of these fi's is a function of just our state variables x1 through xn. Note that this is an autonomous, let me mention that, this is autonomous, as are most of the equations we're studying in this section. And then we're going to let x bar be an equilibrium, which just means that x dot of at that value is equal to 0. Equilibrium, I can spell, of the system. Well, then we can linearize the linearization of the system about our equilibrium, and using a change of variables, let's say u of t is going to be equal to x of t minus x bar. So we're just recentering at, so x bar is the origin, so we're going to consider this as a linear system with, well, the equilibrium at the origin. Recall that the origin is, of course, an equilibrium of any linear, autonomous, non-homogeneous system. This gives a system u dot of t is equal to j times u of t, where j is the Jacobian matrix, where j is the Jacobian matrix of f at our equilibrium. Actually, let me make this 5.5a, since we're going to go back and, this is going to be the theoretical lecture, and then we're going to go back and give some more examples. Okay, so this is the Jacobian matrix, and let me remind you that this is basically just the matrix of all the partial derivatives at the equilibrium. So df1, dx1 through df1, dxn, dfn, dx1, dfn, dxn, and so on. There's a standard Jacobian, and note that assume all partial derivatives are continuous. Derivatives are continuous at x bar. And sometimes we'll actually want to assume that it's or at x bar in an open neighborhood. In an open neighborhood of x bar. And for some of the later theorems, we'll actually assume something stronger, that they're continuous everywhere, but we don't need that because this is entirely a local stability theorem. So given that, then x bar is locally asymptotically stable. If the real parts of all the eigenvalues are less than 0 for all eigenvalues lambda I and unstable if some eigenvalue has a real part greater than 0. And in fact, it turns out that this system will have the same types of classification of behavior as the equivalent linear system, so long as you're hyperbolic. So in the setting where the real part of the eigenvalue is not equal to 0. But we'll get into that a little bit later when we talk specifically about two-dimensional systems. Note that things do go wrong whenever the real part of your eigenvalue is equal to 0. Then you have to do a much more careful case analysis, which we might go into a little bit, but not too much. I'm not going to give a full formal proof of this, but let's give a proof sketch, which is going to be reasonably involved, and so we'll go back to this in a little bit. So we know that x dot of t is approximately, so this is the derivative, not x dot of t. Give me a moment. Oh, sorry, I did mean x dot of t. So x dot of t is, of course, equal to f of x, which is approximately equal to its Taylor series. So f of x bar plus the Jacobian matrix at x bar times x of t minus x bar plus 1/2 of the Hessian matrix x of t minus x bar transpose times the Hessian matrix at x bar times x of t minus x bar plus dot dot dot. And note that if we were to use this theorem with remainder, you would, instead of being at x bar, you would be in some point in the local neighborhood. But we're going to ignore all that for now. So this is the Hessian, because we're only looking at the first order linear approximation, so we can completely ignore that. This is the Jacobian. And this here is equal to 0, because we're linearizing around an equilibrium, which makes life easy. And so this implies that x dot of t is approximately equal to the Jacobian matrix times x of t minus x bar for x of t sufficiently close to x bar. And u dot of t is going to be equal to j of x bar times u of t by a change of variables. And then, well, we know how to solve a system of equations like this given some initial conditions. So this is going to be e to the t j of x bar, so matrix exponential times u of 0. Okay, so now this is one of the reasons why we spend so much time on the matrix exponential, because it allows us to prove things about this, even if it's not necessarily the fastest way of actually solving for a particular problem. So let's assume we have a we can rewrite this in Jordan canonical form, the Jacobian matrix, where B is in Jordan canonical form. So that means that there are eigenvalues along the diagonal and 1 or 0 entries on the row above it, depending on what the Jordan blocks are. So we can decompose B into a diagonal matrix, capital lambda, where capital lambda is a diagonal matrix. And our matrix N is only above, only has entries directly above the diagonal. only has non-zero entries directly above the diagonal, some of which are 1 and some of which are 0, depending corresponding to the Jordan blocks, which are 1 corresponding to Jordan blocks, and some of which are 0 if you actually had eigenvectors, of which are 0. So note that this is not quite the usual n matrix for a single Jordan block, but this is the n matrix for all the Jordan blocks put together. However, it is still nilpotent, which is important. Then we know that e to the tj of x bar is going to be equal to p times the exponential of t lambda plus tn times p inverse, which is equal to, by the properties of the matrix exponential, p times the exponential of t lambda times the exponential of tn times p inverse. And note that n is nilpotent. N is nilpotent. And so is Tn, because, well, that's easy enough to show that if some power of n is equal to 0, then some power of Tn is also equal to 0, because Tn is just the t to the whatever power times n to whatever power. Plus, the power series of exponential of Tn can be cut off after a finite number of terms. After, well, n terms, because after n terms is just 0. So we get that exponential of Tn is equal to the sum from m equals 0 to t minus 1, oh sorry, n minus 1, n minus 1 of t to the m cm, where cm is a m by n matrix. Matrix has no dependence on t. In fact, you can go ahead and write this out. This is actually just equal to 1 over m factorial times n to the m. But that doesn't really matter. So we're going to, all that matters is this is some matrix that has no dependence. That has no dependence on t. Also, exponential of t lambda is a diagonal matrix with terms e to the lambda I t. But we know that the limit as t goes to infinity of e to the minus rt times t to the m is equal to 0 for any r greater than 0 and integer. Integer m, well, we'll say less than n because that's what we know here, but it doesn't really matter unless it's some finite integer. Plus, and you know that when you take a diagonal matrix and multiply it by any other matrix, all you're doing is you're scaling all of the entries of the other matrix by the diagonal terms. And so we're precisely multiplying it by terms of the form e to the minus rt. So thus we know that the limit as t goes to infinity of exponent of t lambda times the exponent of tn is equal to 0. Which implies that the limit as t goes to infinity of the exponent of, of u of t, which is equal to the limit as t goes to infinity of the exponent of tj of x bar times u naught is also equal to 0. Note that, of course, we in order to get from here to here, you have to multiply by p and p inverse, but that doesn't actually change anything since it has no t dependence, and so it still goes to 0. And of course, substituting things in, this implies that the limit as t goes to infinity of x of t is equal to x bar. And this basically proves, so this almost proves the stability. This proves that so long as this proves the stability so long as your eigenvalues all have negative real part, because you're asymptotically going to approach, you're going to get local asymptotic stability because you're asymptotically going to approach your equilibrium x bar. Now, on the other hand, if we had any real part of an eigenvalue be greater than 0, then the limit as t goes to infinity of u of t is going to be equal to infinity if u of 0 is equal to vi, the associated eigenvector. Of course, the linearization breaks down as you get further and further away from x bar. So the linearization breaks down. So you can't actually say it goes to infinity because this is only a local result. So the linearization may break down as x of t minus x bar. The distance from your equilibrium grows. But x of t will still leave a sufficiently small ball. It will still exit a sufficiently small ball around x bar, so it is unstable. So let's see, locally asymptotically stable in the case where all your real parts are less than 0. Okay, so that completes the proof sketch. I went over some of the key steps a little bit quickly, but hopefully you can go back and verify them all more carefully. Okay, so basically what we said there is that once you do the linearization, you just have to look at the eigenvalues of the Jacobian, so long as the eigenvalues are all not equal to 0 or don't have a 0 real part. And of course, this is a class of systems that we're going to give a fancy name to. We're going to call them hyperbolic or non-hyperbolic. So this is definition 5.6, which is if you have this kind of system, let x dot be equal to f of x, have an equilibrium, x bar, so f of x bar is equal to 0, and let J be the Jacobian. Jacobian of f at x bar, when x bar is hyperbolic if all eigenvalues of J have non-zero real part and non-hyperbolic otherwise. And one of the immediate consequences of this is that we can apply this to 2 dimensions. So this is Theorem 5.4 in the book, which the book actually directly proves instead of giving a sketch of the more general proof that we gave for any dimension. So in Theorem 5.4 in the book, they say that x dot is equal, so we have the same setup, x in r squared, and the partial derivatives are continuous. So same setup, derivatives of f are continuous in an open ball, so an open neighborhood of an equilibrium, x bar. Well, len what we can say. Len x bar is locally asymptotically continuous. Stable. If the trace of J is less than 0 and determinant of J is greater than 0, because note that we can use Routh-Hurwitz to show that if that's true, then all the eigenvalues have negative real part. Of course, trace of where J is the Jacobian. Jacobian at x bar. And it is unstable if either of those things is reversed. So if Euler trace of J is greater than 0, or determinant of J is less than 0. Note that we don't actually say anything about the case where either of those is equal to 0. So we talked about things like stable centers for linear systems, and we still have stable centers in these nonlinear systems, but you can't just look at the eigenvalues to figure it out, because the nonlinear term might mess things up. So we'll see an example of this in the next video, where we'll go back through and talk about this in a little bit more concretely with some examples. But this is the theoretical half of local stability of first-order systems. So I will see you in the next video.